Welcome everybody to this plate tectonics review for Lt1. Now this part of the test will be longer than the other parts of the test. This part of the test is one page, it's a front and a back, so one full sheet of paper, 2 pages. So this one will be a little bit longer than the other learning targets. Now first of all, one of the things you're going to have to be able to do is you have to know all the layers of the earth. For example, when it says rocky here, what do you think's behind this? If you said it's the rocky crust, you're right. Now a couple of things that were mentioned in the video that we haven't talked a lot about in class were the Moho discontinuity and the Gutenberg discontinuity. And all these are the areas where scientists believe the crust starts or stops and the mantle starts. And the Gutenberg discontinuity is the border or the transition zone between the mantle and the core. So when it says molten, what do you think's behind here? If you said molten outer core, you're right, and you probably figured out that the bottom one is the inner core. So here's some true and false questions. We'll see if you can get these right. What I would suggest you do is hit pause on the video and see if you can answer these. And then I'm going to go through them and see if you got the answers correct. So a tension force is associated with a divergent plate boundary. So if it's a divergent plate boundary, it's being pulled apart. So think of it like a rubber band. If you pull a rubber band apart, you are going to get tension. So that would definitely be true. The plates move on average of 1 to 25 miles a year. False. They move much, much slower than that, approximately at the rate that your fingernails grow. Convection currents have nothing to do with density. That's absolutely false. Remember, you get the convection currents, or at least scientists believe there's convection currents inside the mantle, and this happens as a result of magma being heated up, and when it gets heated up it becomes less dense than the surrounding magma or material, and then it rises. Now this last question, less dense magma sinks while more dense magma rises, and we kind of answered that with this one. If you think about it, that obviously is false because less dense magma will rise, not sink. Couple more true and false ones. The layer of the earth gets denser as one travels downward. That is definitely true. And the plates are still moving today. That's true. And convergent boundaries are associated with a compression force. So if things are going to, remember, convergent boundary, if things are converging, they're coming together, this would definitely be what? True, false? Did you say true? You're absolutely right. So how did you do on these? Did you get them all right as well? Now here's some multiple choice. What is believed to cause plates to move across the Earth's surface? What is your choice? What do you think? Again, I would hit pause and I would answer these, and then we'll see if we have same answers. So what is believed to cause the plates to move? So what is believed to cause the plates to move across the Earth's surface? It's got to be convection currents, because think about it. Are ocean currents really going to move these giant plates, and are wind currents going to move? No. When an oceanic plate and a continental plate collide, which one usually stays on top? Well, hopefully you said continental plate, because remember, oceanic plates are much denser, they're much heavier, mainly because they're made up of basaltic material. And if you remember basalt from our rock unit, basalt is a dark, heavy rock. So continental plates will stay on top. They're going to be less dense than basaltic type rocks. And this type of rock would be granitic. When two plates collide, the one that is blank usually stays on top. Well, I just answered that. It's the one that's less dense. Okay, so let's move to the next one down. Some more multiple choice ones. The San Andreas Fault is so if you remember, that's one of the most famous examples of these in the world, just because it's on land. Typically this does not happen on land, and is a transform fault boundary. And the Mid-Atlantic Ridge is which one do you think? If you said divergent plate boundary, you are correct, because remember, down the middle of the Atlantic Ocean, the plates are pulling apart, and new magma comes up and forms new earth there. So here's a multiple choice one, or more of a matching than multiple choice. So you should know, and this is all on the layers of the earth, so you should know few key facts. And if you know the key facts for each of the layers of the Earth, you should do fine on this one. Now, what I would always suggest, do the ones you know first. And then if there's some you don't know or are a little confused about, well, now your choices are limited because you did the ones you know first. So mix up the plates. Again, I would pause this, see if you can answer these, and then go through and listen to my explanations and answers. Mix up the plates. The word comes from the Latin word litho. So if you just look at litho, it's a dead giveaway, lithosphere. The thin outer layer of the Earth is the crust. The solid part of the Earth, very dense, made up of iron and nickel. Now it's solid. Iron and nickel, that should be your inner core. Largest layer of the Earth is the mantle. Now, a plastic-like layer of the Earth, the plates right on top of this is actually located within the asthenosphere. Oh, I'm sorry, the asthenosphere is located within the mantle. I had to think about that one for a second. So the answer here should be the asthenosphere. And again, plastic-like, meaning it can bend, it can move. And the liquid layer of the Earth is the outer core. So how'd you do in this one? Did you get them all right? So let's move on. Now, here's one of the short answer questions. And you've known about this question since day one of the unit because I always give you these ahead of time. And hopefully when we review these in class, you'll do a good job with them as well. Now, the Andes Mountains, the Himalayas, and the islands of Japan were all formed at convergent plate boundaries. Explain how the formation of the Andes Mountains, the Himalayas, and the islands of Japan are different. So this word here probably should be differ, how they differ from each other. In other words, discuss the types of plates involved in each location. Now, do you remember where the Andes Mountains are? If you were to look at a map, the Andes Mountains would be in South America. So you've got the South America, you got South America, you've got the Pacific plate right there. So do you remember what type of plate boundaries they are? If not, look it up in your notes for this, practice writing it, and then get it ready for the test. Now, the Andes Mountains were formed by an oceanic continental plate boundary. Do you have to be that specific? No. As long as you said, well, an oceanic continental plate boundary, what type of plate boundary is that going to be? Is that going to be convergent or divergent? If you said convergent, you're exactly right. So it would be formed by a convergent plate boundary. The less dense South American plate is actually riding over the more dense Nazca plate, which is actually sandwiched. If you could look at a map, it's sandwiched between that Pacific plate and that South American plate. And eventually the Nazca plate's going to disappear. And there's a subduction zone here, and one of the things you're going to get are the tall Andes Mountains as a result. Now the Himalaya Mountains, right here. If we remember the Himalaya Mountains, what happened with those is you had India coming into the underside of the Eurasian continent. So you had Eurasia, and then you have India coming up here, and it's actually slid into it. So here you have two continental plates coming together. So it's definitely a convergent plate boundary. Yep. So it's a convergent plate boundary. But do you remember what's the difference between the Andes Mountains and the Himalayas? They're both convergent. Well, this one was an oceanic coming into a continental. This one is two continentals. So when I ask you to tell me how they're different, this is how they're different. They're both convergent, but one's oceanic in the continental, one's continental in the continental. And then finally you have the island of Japan. Again, it's a convergent plate boundary. They all are. It says that right here. But how is it different than the other two? Well, you have oceanic continental, continental, continental. Now you're going to have what? The islands of Japan were formed by basically two oceanic plates coming in together. And as a result, the islands of Japan were formed. And that's why they're very volcanic in nature. And you have some very deep trenches here as a result. You have a subduction zone happening. So how are they all different? Well, you're going to want to talk about these different types of convergent plate boundaries. And that's why we did the plate boundaries activity. This is the one you did with the sub when I was gone that day. If it's a different year, maybe I was here for that if it's not 2013. But that's definitely how they're different. Here we go. Here's our next one. Which layer makes up the lithosphere? Now, if you said the crust, you're right. Okay. Now, if you said the mantle, you're right. It's actually both of them. It's all of the crust and the very top part of the mantle make up the lithosphere. How about this one? Which layer has the lowest temperature? Should be the crust because it's on the surface of the Earth. Which layer has the highest temperature? Well, the further down you go into the planet, the hotter it gets. So you should have the core. And which layer takes up most of the Earth's structure? Well, the largest layer of the Earth is the mantle. So here again, just a little diagram. If you want to stop, pause, study it, you can. Just know that all the lithosphere right here, this is the lithosphere. It's all the crust in the very, very top part of the mantle. And then below that, you actually have the asthenosphere. And then you have the lower mantle. Now, this is one of the things you're going to have to make sure you're able to do on the test. So you did this in Schoology, and I would study Schoology and make sure you get all of these right. So I'm not going to spend a lot of time here in the review going over it. I'm just going to quickly go through and pick these up. So a crustal plate, I see there's a crustal plate right here. Pick up partially molten rock becomes new seafloor. I am going to put this, it doesn't fit, but I'm going to put it right here. Pick up the next one, old ocean floor. I'm going to put it right here because you can see it happening in this area. Crustal plate is right here because you can see it's part of the plate. Ocean floor, I already gave you one, so it's the opposite of that. It's right up here. Pick up the next word. The mantle is way down here because it's deep down. So this diagram really gets you thinking about things. You know where the convection currents are, the conveyor belt. Mid-ocean ridge is going to be right here. A trench forms out of subduction zone. Now here's one of the things. People get confused sometimes. I'm going to put the crustal plate here. I'm going to put the continental crust here. People are wondering, why is this the ocean floor and why is this the continent or the continental floor? Well, look, what's being subducted down underneath? Usually the oceanic plate subducts down underneath the less dense continental plate. So it really gets you thinking about the structure, and you really have to know the material well and be able to do that right. Know that the mid-ocean ridge is a divergent plate boundary. So you're really going to have to know the plate boundaries for this test. Here we have oceanic, and this would be your Japan. So Japan was formed in this way. So this is where your island arc of Japan would form. And you study this one as well. This is two continents coming together. This is your Himalaya Mountains. I might come back to this slide in a few minutes. Oceanic versus continental. And here's where you are. Would form your Andes Mountains. And you're going to get a trench here. And you're going to get a lot of melting going on in that. The less dense material that does melt, because it's going to melt first, is going to come up and form your volcanoes. And know that your San Andreas Fault here is an example of a transform fault boundary. Now the last question I want to go over with in the review is also on the test. Explain why there are few volcanoes in the Himalayas, yet there are so many earthquakes. So let's go back to this slide. What do we know? First of all, in the Himalayas, there's two continental plates coming together right here. Now, one of the things you don't see is you don't see any subduction in this area. So a lot of what's happening is it's crumpling up, it's smashing together. Now, yeah, you do have some subduction going on, I should say that, but you're not going to have those huge trenches here that are really, really deep. So for the most part, as things are sliding by, all that grinding, you're going to get a lot of earthquakes, but because it's two continental plates, you're not going to get much for what? Remember? You're not going to get much for volcanoes. You're not going to get a lot of lava. So there are a few volcanoes in the Himalayas because it's a continental plate boundary. That results in uplift with little or no subduction happening. And there are many earthquakes there because, well, the plates are sliding past each other. It's not going to be a smooth transition. So this is part one review. The other two reviews will be much, much shorter. If you have any questions, as always, please feel free to stop into school and ask me. I'd be willing to help you out wherever I can. Thanks and goodbye.